Okay, we're right at 10 o'clock on the dot, so let's get rolling so we have plenty of time for the discussion. Our first panel of the day is going to be on large loads, and starting from right to left, Lee Bratcher from the Texas Blockchain Council, Katie Coleman from O'Mulvaney and Myers, Ahmed Rashwan from Electric Power Engineers, A.G. Springer from the Electric Reliability Council of Texas, and moderating the panel is Aaron Quigley, Texas Arrays Manager of the Registration and Certification Program. Aaron, take it away.
The introduction. Hopefully everyone can hear me okay. As a reminder, all of our panelists' full bios are available on the event hub on our website. In the interest of time, we'll go ahead and jump right in. Let's set the stage here a little bit. What are the differences in how historical large loads operate compared to the newer large loads such as data centers? And in addition, what do we need to learn about variability in power consumption for large loads, and how does that impact plans to provide service to them? Ahmed, we'll start with you.
Okay, thank you. I'd say the large loads that we're seeing coming onto the grid, or expected to come onto the grid now, have fundamentally different behaviors than the ones we've traditionally seen in the past. Two of note, I think Aaron mentioned one of them being variability, the other one is predictability. Those are two fundamental pieces when you're preparing for operations or you're planning the power system, is understanding those operating behaviors and philosophies and making sure they're well accounted for when you're making decisions. So if we look at initially with variability, there's a couple of items that I think are directly impacted by that. First of all, we'll start light and we'll kind of build into some of the more challenging ones, is just voltage control. Some of these data centers that we're seeing have variability expectations of potentially 30 to 100% consumptions, ramping up in a matter of seconds, back down, then going back up when they're doing training. That's huge. And if you think of a gigawatt facility, that means you could have ramps of 700 megawatts happening every couple of seconds. That's not behavior that we're accustomed to on the system. It's not behavior that we're prepared for on the system at this point. So that's the first point, is from a voltage control perspective, you need to be able to manage that change in voltage that comes as a result of those changes in load levels. Traditionally with loads, we compensate for power factor with capacitors, but capacitor banks are designed to switch in maybe once or twice a day. So when you're thinking from a voltage control philosophy, in this case, you really need to start thinking about dynamic control. So you're gonna need dynamic devices to help manage and follow the load from a reactive perspective. The next thing you think about, obviously, when you have large variabilities like the ones we just discussed, is power quality. So with those changes in consumption comes changes in voltage, as we just discussed. And depending on the frequency of that and the impact, depending on the short circuit level where you're connecting, you could see quite large changes in voltage if they're not well managed. And so certainly power quality and from a flicker perspective on voltage and harmonics distortions that can come through from the type of loads, which are largely electronic, are items that are typically considered but really amplified with these types of loads. With the variability that we just discussed, and I know ERCOT has talked about this, is from a regulation perspective, voltage control as a balancing authority, how do you control that type of ramp? So if you're talking about one facility doing potentially 700 megawatts at any given time, and you start to place really large facilities throughout the state or even anywhere within the nation within a balancing authority's footprint, those can be really, really large ramps. So is there a way to kind of mitigate some of those ramps? And that's something I'll talk about kind of as we go through this. But just understanding the problems now is, if you have 40 gigawatts of data centers, how much variability really is that at any given time that you have to deal with? It's substantial. So traditional methods of regulation won't be enough on their own to manage that level of variability. There needs to be other compensatory mechanisms or discussions with data centers to mitigate that. And now we'll kind of just jump into some of the more, I think, large-scale impacts from variability and integration. The first of which is resonance, which is a little bit of a challenging subject to talk about, but think of, when you talk about a glass, and if you shake it at the right frequency, the glass can explode. There's a really similar concept that you have on the power system where there are natural oscillatory modes across the power system. Depending on where you are in the system, those are different frequencies. Now, if you talk about these facilities bumping up and down at a regular frequency, if those frequencies of their variability match up with the natural system frequencies, you can get what's called resonance on the system. There was an event that happened on the Eastern Interconnection, I believe it was in 2018, where there was a generator in Florida, I think it was in Tampa Electric's footprint, that was varying by just about 40 to 50 megawatts at a frequency of 0.25 from an oscillational perspective. That resulted in 800 megawatts of transfers across the northern part of the eastern interconnection. So it expanded, grew. It resonated with the system's natural frequency. That's something that can happen as well with this potential variability. And the last point that I want to touch on as it relates to the behaviors, and I know we've all heard about this, is the ride-through considerations. So we've seen some events across the power system. ERCOT has certainly documented a large amount of them related to some of the crypto mining loads in Texas. We've seen discussion also about the PJM events, where there's been normally cleared faults that have resulted in widespread loss of load that was not disconnected by configuration. And right now we're talking about a smaller amount that's already been connected. As you expand the amount that we're connecting, if those same ride-through behaviors continue, we could end up with much larger scale losses. So we've seen an 1,800 megawatt loss in PJM, where it was across a bunch of different facilities that were lost through ride-through considerations. As you expand that, that can be substantially more. And when you lose load in a way that you're not expecting, you've postured your system expecting that load to stay online. When it's not, when you actually go through that and it doesn't go the way you expect, you could be exposing yourself to thermal overloads of facilities, transient instability of the system, high voltage considerations, frequency issues. So there's a lot of things that you have to unpack with that. So I think the first thing we'll need to figure out is, what can be done to mitigate some of these issues? And as part of some of the task force I'm involved in, certainly at the ERCOT level with the NERC Large Load Task Force, as well as through the ESIC task forces, there is a concerted effort to figure out what are the drivers behind some of these behaviors, and what are some of the opportunities we can kind of take advantage of to mitigate them at a facility level to start. The next level is also software mitigation. So we've seen some documentation from Google, I believe recently, on opportunities to smoothen out some of that variability through some software mitigation, changing kind of how their algorithms behave. These are kind of incremental opportunities. I don't think they're going to fully get rid of the issues that we're seeing, but they can mitigate the magnitude that we're seeing on the system. And then after that, we'll be able to quantify really what's the size of the problem that we have to deal with when we take care of as much as we can through design considerations. So I'd say overall, fundamentally there is a big difference between the operating behaviors and the transient behaviors of these facilities relative to the ones that we typically are accustomed to.
Great, thank you. Anyone else on the panel have any thoughts?
I'll chime in briefly. Many of you know I represent the traditional industrial community, the trade associations that they're involved in. And if you compare the types of large loads that my clients have, which were traditionally the largest customers on the grid, compared to the new loads, I think Ahmed touched on a few of the differences, but the equipment is fundamentally different. It's more low voltage computing equipment compared to heavy industry manufacturing equipment, and those have different operational characteristics. The size, the amount of load that is looking to site at an individual point of interconnection is much larger. So prior to some of these hyperscaler applications, the largest industrial loads at a single point of interconnection in ERCOT were like 800, and those were outliers. A 200 or 300 megawatt facility was more common. And then, so, there are differences among the computing loads. There are traditional data centers that tend to be very high load factor and don't move around a lot. But with respect to the price responsive loads, which is mostly crypto right now, we're starting to maybe see some AI learning and some other applications that are price responsive. But the homogeneity of the response and how widespread it is very different from traditional industrial loads. So I would say of my client base, we probably have a third that do any really active price response, because remember, they're making widgets. They've got production quotas. They have to be very selective about when they're going to reduce their usage. Whereas some of these new loads today, it is a pure play conversion of electricity into crypto or whatever the output is. And so you see a lot more consistent and broader response to price signals, which creates a different operational challenge than the traditional industrial community.
Thank you. Well, let's go ahead and move on to the next question. Load that is flexible can have powerful benefits to grid operation in managing peak demand, periods of stress, and even emergencies. But certainty about availability is needed, and data center owners have other priorities. How are we working towards common understanding and commitment for mutual benefit of grid operations? AG, will come to you first.
Yeah, and maybe I'm gonna cheat a little bit and tack on something I would have added to the last question, which is there's different timescales of flexibility within these new loads as well, and so these data centers, as Ahmed pointed out, there's variability down to the sub-second level, potentially in the subsynchronous range. There's very fast responses and variability within a matter of seconds. There's longer term variability, so maybe the ability to respond to a dispatch signal over a 5-minute time period, or maybe there's more flexibility to come off the system within longer time period, maybe 10 to 30 minutes. And all of these really need to be accounted for. And with a generator, there's this long-standing relationship with the grid where there's telemetry provided, there's information about the capabilities of the unit that are utilized to both operate the system in real time and also project forward into planning studies and longer-term assessments like that. And I think we're starting to see more of that type of interaction with these new large load customers. Traditionally, that hasn't been necessary to maintain the reliability of the system. But when you start to have these loads that are larger than some generators and can operate either by their design or with a desire to be price responsive in a variable fashion, either measured in cycles or seconds or minutes, more coordination is needed because Ahmed already listed out all the potential impacts of unexpected variation of load, and we've already had a number of different events. We've already talked about the voltage ride-through issue. We keep cataloging additional fault events that lead to load reductions in ERCOT. We've also had an event with a large load that was exhibiting subsynchronous oscillations. Fortunately, it was not near a unit, but had it been, we've seen a growth in co-location in ERCOT, and had it been located behind the meter of a generator, there's the potential for equipment damage there. And we're not capturing any of these in the models for these loads. We're not capturing any of these as a result in future studies, and then some of these variations also get into our ability to accurately forecast load. So we're starting to, the ride-through issue has prompted the DWG large load survey to collect additional information about the ride-through characteristics of these large loads. I think we're going to need more and more coordination, maybe not a direct control relationship with these loads, but we need more information to understand how they operate and what sorts of signals and incentives might lead them to vary that output and how fast. So I see this as very much the beginning of that transformation, because that's certainly not where we are today.
Lee, I'm interested in your perspective on that.
Yeah, so we represent the Bitcoin mining industry and increasingly part of the AI industry because some AI companies are acquiring Bitcoin mining companies wholesale. CoreWeave just bought Core Scientific. The sale isn't final, but they've announced an acquisition as of a few weeks ago. And in some cases, Bitcoin miners are turning to host AI. But regardless, there is about 4,000 megawatts, and that number varies from time to time based upon what's approved and what's energized and how much is running at any given time. But quite a bit of Bitcoin mining in ERCOT. And as AG said, the name of the game is growing certainty around when that curtailment is going to happen and the communication, getting these loads ideally into SCED so that there's like a precise known time when the price hits this, the load's going to do that. So we've been working towards that direction for a lot of reasons. These loads Can't quite get into SCED yet, but that is a goal. I think as we get more data around where the break-even point is for a particular Bitcoin miner, and the nice thing is the miners, they have a break-even point that is based upon the price of Bitcoin, the price of power, the efficiency of their machines, and the difficulty of the network. So it is mathematically possible to compute what those break-even points are, and ERCOT has done a really good job of modeling that data. It's very difficult for, the other factor there is how long a machine will be down, and so that's kind of difficult to add. If you have a WhatsMiner machine, it takes a little bit longer to reboot, so that means your break-even point gets a little bit higher. If you're doing air-cooled Bitcoin mining, which is just a fan blowing over chips, then you have maybe a little bit of damage to the machine every time you curtail, and may or may not have damage. So we'll call it, adds 1 to 2% increase in your break-even point because you have to calculate the economic costs of, curtailing and maybe risking 1% of your mining machines receiving a little bit of damage because the boards are heating. They're hot and then they cool really quickly and then they heat back up, and that could cause some issues with the chips on the boards. So while there are some precise calculations that can be made about when a miner will curtail at 100 megawatts, or $100 a megawatt hour, or $120 a megawatt hour, there are some imprecise things that create a range. And so ERCOT is kind of looking at this and saying, all right, we see some people on this end are curtailing at $70 a megawatt hour, and then on the upper end, it's, call it $150 a megawatt hour, $200 a megawatt hour. And why would there be such a range if they're all mining on the Bitcoin network? Well, it's all those things that I just discussed. It could be that on the cheaper end, they're using a Bitmain machine, which is faster to reboot. Or maybe they're immersed in dielectric fluid, and so they don't have to worry as much about the heat and the damage to the boards as an air-cooled machine. So that's why you could see a range, and we're working on dialing that in, and I think more communication is better, obviously, and so as we have site-specific information, ERCOT can have a sense of past data. Okay, this is an immersion facility. They have Bitmain machines. They're probably going to curtail around $90 a megawatt hour. This is air-cooled. They might curtail. And barring all that, SCED is optimal because then ERCOT knows. But there are still some obstacles to getting all this load into SCED. And so that kind of maybe gives you a sense of why Bitcoin miners aren't all curtailing exactly at the same price. But on the opportunity side, I guess that's on the risk side and like the need for greater communication with ERCOT. On the opportunity side, we have 4,000 megawatts of load in Texas that can be extremely price responsive in a way that can be very beneficial for reliability. If we got all this dialed in, imagine all of that load was in SCED. All of that load had, say 60, 70, percent the ability to ride through a fault when voltage sags to 60% of normal or 70% of normal. So if we fix these issues, you really have a powerful tool for grid reliability that is just purely driven by market dynamics, and that's something that has never existed that I'm aware of.
All right, thank you.
Aaron, if I can
Sure.
add just a point, because I'm happy we talked about markets because they really are going to be the enabler for the flexibility that we're looking to get out of these facilities. And it's actually something we're going to need to invest in. There's some market designs that have really been that have been set up in a way that they're focused on or they're enabling the current system that we have. And we need to make the transition towards understanding what are the drivers of these other facilities that we're adding online. I'll just provide one example, then maybe talk about a challenge that I see coming. There was a really hot day, I think it was last summer in ERCOT, and there was one of the crypto facilities that stayed online unexpectedly. And some discussion happened thereafter, and they were asked, well, why did you stay online during that time? And, well, because we scheduled for reserves. So, you scheduled the load for reserve, so they stayed online. Is that the right outcome from the market perspective? Is that what we're looking to do, is keep load online when it's really hot and we could, leverage other opportunities to serve. So one thing I do want to talk about specifically for data centers, it's different than other facilities, is their compute loads. And they're not necessarily tied to the location where they're built. There's data centers across the nation, and compute loads can be routed anywhere. Depends on the type of transaction that you're doing. So if it's a credit card transaction and latency is really important, maybe they'll use a local one. If it's not important, they could go anywhere. And so now you start to think of their participation in markets. And when we design markets, we design them at a local level. So you have your PJM market, your MISO market, your Texas market. You're not looking at external price to forecast load. But these facilities could be making decisions on where they consume based on the entire landscape of the nation. They could say, you know what, California looks great from hours 3 to 6. And then PJM looks really great after that, but then they get expensive. MISO's got a lot of wind, we're gonna go to them. Later in the day, we're gonna go to Texas. They could plan their operations differently if they have that flexibility. So with flexibility, which is great for us at the reliability level, it also provides them flexibility to do things that are not typically considered in our own forecasts. So how do we consider forecasting now at a larger level for these types of facilities is a challenge that I see coming up. And us trying to really understand, are there constraints we have to put around that level of changing between different jurisdictions throughout the day?
Yeah, I think there's also, to tack on to that, there's also the potential for linked compute jobs between multiple data center facilities where, the compute going on at one facility is dependent on potentially compute going on at another facility. And, when we start to talk about forecasting or, even something as fundamental to reliable operations as definition of contingency. So if we define, there's a gigawatt facility that's tapped off this line, if we lose the line, well, we are aware we're going to lose that load. But if there is linked compute at another large data center elsewhere in the system, we may lose more load than we actually projected. And that, there are a number of, you mentioned market design, but also our, reliability processes and design, I think are also likely going to need to evolve to accommodate these loads as well.
Okay, thank you. I want to go back a little bit to a point that AG brought up, which is that co-location of large loads with dedicated generation sources is a growing trend that we're seeing, which presents interesting possibilities, but also logistical challenges. I'm interested in what would make these types of projects attractive to developers in the Texas interconnection versus elsewhere. And Katie, I'll come to you first.
Sure. So this is not a new model. It's just being used in new ways and on a broader scale. So co-location with generation is something that the industrial community's been doing since the 70s, really since PURPA. But I think what's happening is you're seeing less of the historical model of synergies between a cogeneration unit and an industrial process, and more just opportunistic opportunities where there's infrastructure there. A quick interconnection is key for a lot of these applications. And so the existing infrastructure, a transmission level interconnection is hugely important. And then you often have certain types of economically challenged generators in ERCOT, particularly renewables that are in transmission constrained regions, where there can be a win-win scenario where a computing company can site next to that generator, take the power in times when it would have been curtailed otherwise, and then leave the resource available to the grid when it is economically viable. So there's a lot of new ways of thinking about this, but it is a very old construct. ERCOT's been modeling these types of co-located arrangements again since ERCOT was what it is today in the early 2000s. So it's not something new, but it's on a new scale. From a market design standpoint, so this is not so much a reliability issue, but it can be a very good, I guess it is ultimately a reliability issue. It can be a very supportive feature for resource adequacy. You see a lot of thermal generation units even that are looking at not being competitive relative to renewables and newer units. And if they can get a credit-worthy large off-taker at their site, it can give them the cash flow to make upgrades, to make expansions, to keep that facility in operation longer. And so we're seeing a lot of even traditional generators that were standalone generators that are very interested in this. And so it is something that can be supportive of resource adequacy. I think the challenge is just, I think ERCOT is, their preference is, you've got a point of interconnection that's a standalone load and a point of interconnection that's a standalone generator. That's simpler. It's easier to predict what's going to happen there than a combined load. But one point that's been coming to my mind throughout this conversation is these are all new versions of old issues, right? Like I've been dealing with my clients getting surveys from ERCOT about how their private use networks are going to operate under certain scenarios my entire career. And one of the first, experiences I had in this job was a client coming to me and saying, well, we've been asked how many times we're going to curtail to try to avoid 4CP. And they're like, we don't know how to answer this. What time of the month is it? How many times have we already curtailed? Have we met our production quotas? There's all these factors that make every opportunity different. But over time, I think ERCOT's been able to learn from the history. They're pretty good at modeling what private use networks are going to do across peak conditions now. I think part of this is just we don't have the background and the information on the behavior of these loads yet. One of the things that came out of the Large Load Task Force is, which surprised me, ERCOT doesn't even know, or they're starting to now, but they didn't even know, like they can see the loads in the model, but they don't know what type of businesses those are. That blew my mind. That seems like step one, right? But there's a left-hand, right-hand thing between the information that the retail providers have and even what the utilities have, much less ERCOT. So just identifying what those loads are, even in a co-location scenario, I think will really help those to be more predictable in the future.
Yeah, I think with the load classifications too, there's also, many customers desire confidentiality too, and that has been another barrier. But yeah, I think Katie's absolutely right. There are many of these reliability issues that we have seen before, but mainly on the generation side. So if we talk about things like ride-through, we've really grappled with that problem for the last 15, 20 years with inverter-based resources, and now we're seeing large-scale, effectively inverter-based load. The problems are very similar though. In terms of resource adequacy, one other just point I do want to make is we have been hearing from industry that a lot of these loads are locating with assets that are curtailed, and so they're using up capacity that would otherwise be stranded. And I would say that is true, that is the characteristic of a lot of the assets we're seeing. But in general, these facilities are coming and consuming the energy full time, and so I don't think I necessarily agree that adding large loads at existing generation facilities is a net positive for resource adequacy, because whether or not we consider a private use network to be sort of a dedicated generation load cluster, or whether or not we, the physics is still, it's a generation and new load that's come onto the system. And so, I think long term, while I do think that there is time periods where the co-located load is allowing for generation production that would otherwise would be stranded, and therefore there's additional potential generation available to serve the rest of the system. I think over the year in aggregate that you're still seeing these large users come faster than we're seeing new generation get built, and that is a real concern for resource adequacy.
So Katie, going back to the point that you made about not necessarily having all of the information about these, do you have any thoughts on how the owners of the large loads can better engage with utilities on issues like modeling, load performance characteristics?
One of the sort of issues we've been trying to work through in this conversation is a desire to directly register and regulate and interact with the customers. And I think that is a little bit of an uphill battle. Historically, if you're just a pure customer, the grid exists to provide power to you. And that's the same whether you're a residential or a business customer. You're not supposed to be a regulated, registered entity historically. And so I think there's been a lot of pushback when the approach has been trying to register these loads, put operational requirements on them. I mean, we're not seeing other jurisdictions doing that, although I know a lot of them are having these same discussions. But our preference has always been you can get to the same place through the utility. The utilities have direct relationships with these customers. They have a contract with the customers. So if you think about, again, historical large industrials, we sign facilities extension agreements with the utilities. It's a contract. There are specifications in there about what our equipment has to look like, how it has to perform. I think you can repurpose those types of tools to mostly get where you need to be without having direct regulation of the customers. And I think that you're going to get a lot less pushback with that kind of approach.
Thank you. Let's move on to the next question. Do most of these facilities plan to have significant backup generation? And if so, does that generation cover much of the facility's needs temporarily? Or is it more of a minimal critical function service? And additionally, how are utilities and power suppliers considering this in developing plans to serve these facilities? AG, I'll come to you first.
So I think our experience so far has been it's a mix. We're seeing a lot of the hyperscalers are coming with enough backup generation to serve their entire facility plus redundancy, but that is intended to be an emergency service for the facility when grid power is unavailable. And so, and typically there's also UPS and sufficient to allow that transition to happen. And so, this presents, it's another kind of case where a lot of our existing processes and market registration and reliability processes really weren't designed for this kind of model where we have large amounts of generation, but it's not intended to ever be synchronously connected to the grid. And so, in those cases, we're really treating the load as just a load, and that backup generation is really not accounted for in the interconnection studies because it's not ever going to be injecting to the grid or even synchronously connected. And so even when a facility has switched its backup power, it has left the grid, for all intents and purposes. Now, that gets more complicated when we start to talk about things like voltage ride-through, where the UPS is maybe an asset in improving the performance of the facility. Potentially, we've seen some customers explore, locating some amount of battery storage on the system that might be used to improve things like ride-through performance. And in those cases, that battery may be synchronously connected to the system. And so the question kind of becomes, well, it's not a resource. It's not going to be a generating asset. It's not going to participate in the ancillary service markets. But we are going to have a physical interaction. And so, how do we model that, and how do we structure the interconnection process and study so that we can get that on quickly? There's quite a bit of change. I think I may have wandered away from the question a little bit, but it's a range. Our experience with crypto mining has been there's not that backup power, I think maybe just to kind of close out my thoughts is just I think over the next 5-10 years we're going to see some changes in registration options and ERCOT market design potentially to accommodate these facilities that are coming with such large backups.
Yeah, Ahmed, I saw you nodding a lot. Did you have anything?
Yeah, I was thinking mostly on the modeling side as well. And I think when we're doing kind of these assessments, just building on what we had mentioned, Katie, sometimes the applicants don't know what type of facilities they're looking to connect. So you have real estate organizations, you have a rancher who's got a line in their backyard. Oh yeah, there's a spectrum of applicants for load facilities. And they're saying, well, how much can I connect at this location? I'd like to connect a data center. And then after that, figure out who's going to host it, who's going to be there. And so when you ask them for a model, so first of all, most of them don't understand what a power system model is. The ones that do will also tell you, I'm not sure what type of facility I'm hosting, whether it's going to be a normal AI data center, a normal data center that processes transactions, just things that happen online, or is it going to be an AI training facility, which is a very different model. So they don't actually have that information. So we're actually at a really interesting point on the modeling side where there's few and far between models available. Sometimes, as AJ mentioned, there's some concerns about sharing models. So some of the developers actually don't want to share proprietary information. unless they have to, and if they do, they give it to us in black boxes. And on top of that, there's uncertainty about the type of facility. So modeling, although really critical right now, seems to be a little bit of an enigma in getting the right information.
Thank you. So Katie, I'm interested, how does federal and state recent activity legislatively affect these issues?
Well, certainly at the state level, there was a big piece of legislation passed recently, Senate Bill 6. I think that's probably more than any federal activity. I think that's going to be the biggest impact in Texas. And I think a lot of what was codified in that bill gave direction on things that were already under consideration. So trying to address, for example, some of the things that Ahmed mentioned about it. A lot of this load is coming from developers putting interconnection requests in to try to see how big of a load they can interconnect at a certain point, and they don't even have a customer identified yet. And I think there's a big portion of the load forecast that is that type of behavior, and some of those are going to make and some of them aren't. But I may be skipping ahead to another question, but there have been a variety of studies from consulting firms about what this demand is going to look like. And one of the things that seems to be a real limiting factor is chip availability. There was another study that came out just in the last couple days showing that in order to meet some of these forecasts for the US, we'd have to get 90% of the available chips, whereas we've historically been less than 50%. So these numbers just, they're not going to pan out, but we don't exactly know what's going to happen. And so I think that's causing some consternation. But I mean, I do think that not knowing who the customer is creates operational challenges. I'll tell you, anytime I ask somebody who the customer is going to be, they always have a very confident answer that it's Google or Amazon. Every single site that's interconnecting, you hear that it's Google or Amazon. I'm sorry, I forgot where I was going with this. What was the original?
Just about any state and federal
SB6,
legislation. Yeah.
right. So SB6 addresses some of that with additional financial security requirements. So that's something that I think was lacking. It was pretty easy to just get an interconnection study done by the utility. They were free for a long time. So additional study fees and then financial security that's tied to the size of the load to say, if you're going to come, say you're connecting a 2 gigawatt load, you're going to have to put money behind that to make sure that it's real. So I think some of that will be helpful. The other two, I would say, big operational features of Senate Bill 6, one is directed at, I would say, more computing loads. One is all transmission level loads. There is a new requirement in Senate Bill 6 to disclose backup generation. So this is not a private use network like synchronous gas generation. This is true, diesel gen sets that are not operating in parallel to the system. That's never really had to be disclosed to ERCOT. And so part of SB6 is requiring disclosure of those facilities and giving ERCOT and the utilities the operational ability to turn sites off that have enough backup to cover at least 50% of their load prior to going into broader firm load shed. That's a major, major change. And it's tailored toward these types of scenarios you're talking about, where it's backup gen truly for emergencies, but this is an emergency and it's trying to target those situations. The other thing is, historically, there has been a reluctance to curtail transmission level loads during EEA. It's been done on a voluntary basis. So those of you that remember all of the URI litigation, there was a lot of discussion about how the transmission level loads were, they got phone calls and they were told, reduce your load, and they did substantially, but there's not a switch you can flip or any operational control to make sure that that's happening. That's something that Senate Bill 6 requires. So it goes even beyond the sites with backup generation. It's any transmission connected load. Of course, my clients hate this. They really did not like that provision of the bill. Of course, you would rather not be subjected to potential firm load shed risk, but it's unavoidable. The level of transmission level load that's coming on relative to smaller distribution level load, you're not going to be able to meet load shed obligations in a lot of scenarios. So that was unavoidable. So I would say those were some of the bigger features of SB6, and I think it was building on a lot of things that were discussed in the Large Flexible Load Task Force at ERCOT. But it was helpful because it's the legislature saying, okay, we've heard this discussion, and this is the direction that we want people to go. Because otherwise, with everybody in the stakeholder process that's got different interests, you can kind of get into deadlock, right? So I think it's going to provide some real guidance going forward on how to manage these issues.
Thank you. Lee, did you have something you want to share?
Sure. I'd add to what Katie was saying. So a couple of points on load shed. I think what wasn't codified in the bill, but I think is what's important to you all and all of us, is updating load shed tables for price-sensitive loads. When a price-sensitive load goes down, or not goes down, but curtails, we need to make sure that the load shed table is updated proportionally so that muni or co-op or whatever, that region isn't kind of hamstrung and having to deal with a load shed table without that load on, so they don't really have that load to bring down. So basically kind of having a system or a function where if there is a price-sensitive load, you recalculate the load shed table. And part of that comes to another point that I thought about making earlier when AG was talking about the reliability concerns, is we need a non-firm load category. And I think right now, NERC and ERCOT especially only has a firm load category, and that's been reasonable for decades. But at this juncture, I think a non-firm load category would permit these kinds of adjustments on load shed tables. It would permit savings on transmission and planning, and really make a lot of people's lives easier if there existed a non-firm load category. So on SB6, our members are not worried about a remote disconnect or having a ability to open the breaker, because we plan, if we're not off at those kinds of emergency levels, then it's a really bad economic decision, and everyone wants to be off when prices are certainly $1,000 a megawatt hour, or else they're losing money by the second. So there were pieces of SB6 that were concerning to us, but certainly the remote breaker, the remote disconnect was not one of them. And I think all of us agree that clearing out the interconnection queue of phantom load was the most important part of that bill, and something that everybody agreed. We gotta get ERCOT a clearer picture of what load is coming. It's certainly not 150 gigawatts by 2030. And then, of course, there are some pieces about SB6 that we were a little bit uncomfortable with, but I think that could be said of everybody. You're never going to get a piece of legislation that everyone agrees to.
If I could just add on the cost allocation piece. So, and I know that this was mentioned in the prior panel too, it's time to have that discussion again, but I really believe that refining how we plan for these loads is a big part of preventing stranded costs around the loads. So there's a lot of discussion about 4CP. If you look at historical studies from ERCOT about the quantity of 4CP, it's usually 4,000 or 5,000 megawatts. It is not a big number. People think it's like the entire industrial community turning off. It's a mix of industrial accounts and municipally owned utilities, cooperatives, residential. So it's a broad base of customers, and it's only about 5 gigawatts. So the cost shifting of that, I think, is blown a little bit out of proportion. But nevertheless, it is time to look at that issue again. But the bigger issue is, I think, what Lee is touching on, which is right now we plan for all load as if it's firm, and if it needs enough transmission to serve the full load across the peak, and that's just not true. And we've got to find a way to sharpen our pencils on that. Same thing with co-located load and generation. Right now, a utility plans to serve that load as if it's the gross generation capability and the gross load capability, and the reality is it's likely to be zero. And so that's how stranded costs are being created, and we would really like to get a better approach to modeling those scenarios, and I think that's going to be a big part of keeping transmission costs down.
Yeah, I think I'll just maybe add a couple of thoughts to what Katie just said. I think the devil's in the details on a lot of the points that she just made. It is true that if you bring a new large load to the system and an equal amount of generation, that for normal operating conditions, the net impact is no load drawn from the system and no generation injected. But then we start to get into details, and so if we were to give that kind of treatment to that in the planning process, well, I have yet to talk to an end-use data center customer looking at that type of arrangement that didn't expect either service continuously when the generator was out, or at least service long enough to execute a controlled shutdown of the facility. And so, unfortunately, we don't plan for the 99% of the time. We plan for how are we going to have to operate in that 1% of contingency. And so that's why that methodology exists the way that it does today. I think if we can get to a point where we truly can have that assurance that the load is going to be, I put in air quotes, never impacting the system, then I think if we can define what that really looks like, maybe there's potential to modify the processes. The same is true with treating a load as non-firm in a planning horizon. We've kind of talked to several points in this panel about how there generally has not been, and many customers don't want to have a direct relationship with ERCOT. I don't see how we get to a place where we're treating a load as non-firm without some sort of interaction there, because otherwise, how do we know when that load is not going to be there? If we plan for the load not to be there with some level of assumptions, but the load has no obligation to meet those assumptions, then again, that's a potential risk to reliability. So I think there is a path to get there, and I really do want to emphasize too that ERCOT, in addition to the other folks on this panel, there is a way for the interaction between these loads and the system to be a benefit to reliability, but I just don't see how we're going to get there with this sort of traditional model of a load customer having no impact or no interaction with the grid operator. I think that has worked in the past, but when you really are talking about loads that are 1-2 gigawatts and operate in a way that is much kind of closer to that of a generator than a traditional load, I just don't see how we get there without having some level of interaction and responsibility there.
Yeah. Lee, go ahead.
I'll add, I completely agree with AG. I think if there were to be a non-firm category created, that load would have to be far more transparent with ERCOT, would have to kind of pierce the veil of that, that load that is typically interacted with ERCOT through the utility. They would have to directly make some concessions related to their transparency, what information they share with ERCOT, and probably some contractual obligations. So I think if there was that non-firm category, there are price-sensitive loads that would be willing to make that those concessions, and there's probably some loads that aren't, and they'll just stay firm. I don't know if you agree.
Right, and there are instances today where a load is choosing to have a direct relationship with ERCOT and registering, and so it's not that that never happens, but if somebody just wants to be a regular old manufacturer and not be, told exactly how to operate their facilities, that needs to remain an option. But it doesn't mean that there can't be other options. What Lee's referencing is there can be big benefits to being treated as non-firm in terms of interconnection speed, and I think as Senate Bill 6 is implemented and there's costs associated with interconnecting a large load, if you're willing to stand up and say, I'm not going to be this size of a load when it matters, and I'm going to make sure that I have the equipment or software in place to prevent that, then you can avoid some costs. And so there are going to be benefits to being treated that way that could induce somebody to interact directly with ERCOT.
Just a couple of thoughts on that. There's constructs within the generation interconnection environment that we can build on from these things. So Energy Resource Integration Service, which is largely outside of Texas because Texas Connect and Manage, but the other jurisdictions do have that construct where you determine what level of service that you're looking for. One thing though to note is with all these loads that are looking to connect, if everyone decides to have non-firm service, eventually everyone's not going to get service. I think it's going to become very challenging. So just with the amount of interest, I'm saying that there's going to need to be some boundaries on how many facilities can realistically connect as non-firm to balance the expectation they do get some service and that ERCOT can actually manage the situation. Because if they're dispatching every load down every hour, it just creates congestion. So I agree with the concept. I think it's a really great one for us to explore with that kind of right consideration built around it to make sure it's practically implementable.
Yeah, and how do we also ensure that if we have more and more non-firm load, that we're still building out the transmission system to serve the load growth overall? That's been as we've talked about this topic, that keeps coming up is, if we treat the load as able to be shut off in a planning study, well, then that also masks any kind of congestion that load might be causing. So, these are all issues that we're grappling.
I think that's a really good point, and I think you could manage that with how uncomfortable you make it to be in that category. If you're not getting any load that wants to be non-firm, then it's too uncomfortable. If you're getting too much, then it's too easy, and perhaps the amount of you can almost balance that like a market in a sense, how much demand and supply and how much is coming in.
Yeah, and going back a little bit, I know you mentioned, building additional transmission. Katie earlier mentioned chip availability, but yeah, I'm wondering from the flip side of it, how is the tightening supply chain for electrical materials affecting the ability to build these projects, to provide power and deliver it to large load megacenters? And I think AJ, I'll start with you.
Yeah, I'll say that it is impacting. I don't think ERCOT has a really good handle on just how much. We have a lot of anecdotal discussions with the wires companies, with generation developers for sure. But we're definitely seeing longer lead times on key items, so transformers, turbines, things like that. But I think for the large load customers, that's one aspect that we don't have good visibility into right now. I mean, Katie mentioned the amount of chips that would have to be procured to really build out what's projected, and we agree. We don't think that all of that load in the queue is ever going to get built. The challenge for us is we don't know who actually has the contracts in place to purchase the key equipment already, and I think as the load interconnection process evolves, I think that's something that could help bring some sanity to it. Is better visibility of, much like with a generation interconnection, you have to meet certain milestones demonstrating site control and permitting and things like that. Do we need that for large load customers as well? Because we don't have good insight into, how real are some of the numbers, but we don't know who is more real than others in many cases.
Yeah. Katie, I was going to
Well, yeah, I was going to say that you mentioned a couple things that were also required now under Senate Bill 6, like proof of site control, some things like that will hopefully, call some of the speculation. But even with that, then you maybe get only, serious developers, but which projects are going to have access to the chips and the equipment and all that, that is still uncertain. And when location is so important, it's very hard to manage, because all you can do right now is say, we think X% of this is going to come, and give it like a system-wide haircut, but you don't know which locations it's going to, are going to make or not, and that's an ongoing challenge.
Yes. And I'll just add too, the loads are so large that even one deciding to site in an area or not can potentially change the dynamics of the whole area, and so that's a real challenge.
All right, thank you. I think we have a little bit of extra time if we want to go to some of the Slido questions, if we've gotten any. All right, is the current ancillary services market construct adequate for addressing the reliability needs of ERCOT for serving these new large loads? I think I'll come to you, AJ.
Yeah, I bet there'll be several folks who have something to say about that. I think the answer is no. I think in a lot of the recent discussion around voltage ride-through, I think there's the potential for an ancillary service product that is fast responding to deal with sudden loss of load on the system. The one thing I want to emphasize there is that I think ERCOT views changes to the ancillary service market as a piece of the problem. Just like transmission upgrades to the system, another piece of how we're going to solve some of these challenges that we talked about today. But I think one of the real conclusions that we have come to is that it's not possible to strengthen the grid so much that the current model of how we deal with how loads are served on the system is going to work. And I think the same is true. Is there, we can't solve this entirely by creating a new market construct. But I think that both of those things have a piece to play with this.
Thank you. We can go to the next question. Is ERCOT seeing an increase in CLR applications after Lancium patent issue was resolved?
I am not the right person to answer that question. It's just not something I look at day to day. So I don't know. I think one of the other things we'll be watching for is not just with the Lancium patent issue being resolved, but also next year we're hoping to see NPR 1188 implemented, which will create some changes to how CLRs operate and are settled. They'll receive nodal settlement. Does that incentivize more registration as well is something we'll be watching. So sorry, I answered your question with a question there. But
I'll jump in on that one too and just say, a lot of the Bitcoin miners want to be in CLR, but there's a couple things. The Lancium patent being sort of open sourced or given to ERCOT was a really positive step. You also had the primary frequency response requirement, which not all Bitcoin miners can meet. That's getting taken care of, which is another leg of the stool. The third thing is what AG mentioned is the economics of it. It just doesn't make sense to offer in right now. And I know the argument is, well, why don't you just put a $5,000 bid in? And so you're in CLR, but that's just not helpful, I don't think. And so I think the economics of being in CLR need to improve before you see more people jumping in.
All right. My next question, does anyone on the panel have an estimate of the % of annual generation that Bitcoin and AI are using in ERCOT right now?
I mean, you could probably express that as demand. I don't know the number, but AG, you might know how much demand.
yeah, I think there's close to 5.5 gigawatts operational right now, but I don't have a breakdown on how much. It's a mix of Bitcoin and AI. So you can kind of calculate it as a percentage of the generation mix.
All right. Is the 75 megawatt threshold for large loads set in ERCOT proper, or does it need to be reviewed often? What is magical about 75 in terms of reliability?
So the 75 that line was established fairly early on in the Large Flexible Load Task Force, and it really was kind of the point at which the wires companies expected to have, almost certainly to have to upgrade their facilities to serve that load. And so that drew the initial line. I wouldn't say 75 is magical, but I will say this, that, this is something that has been a discussion point in the NERC Large Load Task Force, that, the term large really probably is best measured relative to the size of the system. So while a 1,000 megawatt load is large in terms of impact on things like frequency stability in the ERCOT system, if we were to connect that same size facility in the Eastern Interconnection, the impact is going to be less just due to the much larger size of the system. So I think potentially it could be reviewed often as the system grows. Potentially, the impact of a 75 megawatt load will decrease relative to the size of the system. I think we have to balance that against needing to give developers and planners some certainty of what we're going to consider a large load, and therefore is going to get subject to extra scrutiny. If that number can vary over time, that also makes it harder to develop and plan. So, you just have to balance those interests.
So I think for some applications, 75 megawatts is probably the right number. For others, it probably could be a lot higher. Remember that number was set for the interim study process for large loads, and the problem that was initially being solved there was the speed of interconnection. So ERCOT had a process for looking at larger loads that were going to take at least 2 years to interconnect, because those were getting picked up in the utility forecasts and could be studied. But a lot of these new types of loads can interconnect, if they're allowed, in like 6 months, right? And so they were kind of flying under the radar. And so the initial question was, well, what is the threshold that impacts the transmission system, like AG mentioned? And 75 megawatts is probably right for that. If you're talking about other things like contingency analysis and operational impacts, even today, 75 megawatts is not a material load for those types of purposes often in ERCOT. And historically, industrial facilities, like I said, many of them are 200-300 megawatts, and there have not been issues there. So I think there may eventually be different thresholds for different purposes, but we're still, again, kind of learning what the impacts of these sizes are.
Yeah, thank you. Unfortunately, I think we're at time for the panel today. I know you mentioned the Large Load Task Force. Just before we wrap up, I want to say that the next meeting is next Thursday, July 24th, so should have the results of the first white paper at that point. So if anyone is interested, please tune in. And thank you all on the panel for your time today. I hope everyone has a great rest of the workshop.
Thank you, Aaron, and thank you to all of our panelists. That was a great discussion. It's time for another break. We will be back for the second panel at 11:10.